Lowest of them all. Hit it, Meredith.
The lowest of them all?
Yeah. Na is less than. Nikki in the same row.
Boron.
Boron is next. Allison.
Oxygen.
Oxygen. Charles. You only have one left. Fluorine, okay. All right, and we got him right. Okay, and it's the same reason that as you go down a family, it's a distance effect, because you're trying to attract, but you can only attract to your outermost level, okay, because everything else is full. And so a distance, attraction falls off really rapidly with distance. So, it's a distance effect versus as you go across a period, effective nuclear charge is increasing. More positive charge attracts together. Okay, now let's take a look at this very last section. Ionic size, and there is no arrow system really for ionic size. And what I want to do is I'm going to break it down into 3 parts to make it simpler for you. So here is part 1. We are going to compare neutral atom to its own cation. Compare neutral atom to its own cation. Okay, so let's do this. It's this sort of comparison. We're not comparing this cation with this cation, and I'm not comparing neutral atoms, say, with the calcium cation. You've got to compare it only to itself. When you are working with the ions, since we do not have an arrow system, okay, red flag this. This thing right here is for neutral atoms only. That's a point of confusion for students. Neutral atoms only. This is when we start talking ions. Okay, your first line of defense, or your first thing you're going to attack with, is electron configuration. And so, let's work. When you're talking ions, only the ions, we're going to think electron configuration. Okay, Alex, can you give me the electron configuration of sodium? Long way.
Long way. 1s2, 2s2, 2p6, 3s1.
3s1. Okay. Can we give her full credit? Okay. Let's do the sodium ion. Liz, hit it.
1s2, 2s2, 2p6.
That's it. Okay. This should give you the answer. Which is the larger of the two? Russell, where do you put your money? Which is the larger of the two?
The regular one.
Okay, and why?
Because it has it goes to 3.
Yeah. This one's only the first energy level, the second energy level. Okay, this guy's out on the third. And when you make that cation, you lose an entire major level for being occupied. Brittany, did you have a question, or were you going to answer? Okay, so we can make a generalization here, and very seldom in chemistry do I get to say always. But neutral atom is always larger than its own cation. Okay? Neutral atom is always larger than its own cation. You might try another couple on your own, like calcium and calcium plus 2.
I'm sorry, but what are we solving for?
Who's larger?
Who's
larger, or who's smaller? So we're just comparing sizes.
So it's kind of just using the chart, but
You use your electron configurations if you're talking. Anytime you've got an ion involved, your first line of attack is electron configurations. And this is your tiebreaker.
we can't use the chart because it's neutral.
No, we don't have a chart for this one.
Oh.
The chart's only for neutrals, yeah. Okay, now, the next part. 2. Let's compare neutral atom with its own anion. Okay, since we're talking ions, then we want to think electron configuration. So let me just pick a couple. Now, notice when I say its own anion or its own cation, I am not just putting some charge up here at random, because we know, for those representatives anyway, they only take on one charge. Like if you have something in the 1A family, if it forms an ion, it's always what charge? Plus 1. If you're in the 2A, it is always what charge? Plus 2, when they form ions. Okay, and so forth. So we know a lot of these already. So we know fluorine, being a halogen, that whole family is going to gain 1 and become the -1 anion. Okay, electron configurations here. Timothy, hit it for fluorine neutral.
1s2, 2s2, 3p6,
Wait, sure you want 3?
2,
2, P. Okay, here, I'll give you a visual.
5.
Okay, 5, exactly. All right, that's our electron configuration. Okay, Hina, hit it for this one.
1s2, 2s2, 2p6.
Perfect. Okay, the electron configuration has failed us because we're on the second major level is our outermost. Second major level is our outermost. We tried, it didn't work this time. When your back's against the wall and the electron configuration doesn't work, we're going to play what I call the numbers game. Okay, so let's come over here. Protons and electrons. Protons and electrons. Remember how we did this, I think, back in chapter 2? But back then, I was going protons, neutrons, electrons. But neutrons are neutral. They're not going to have anything to do with attracting and making smaller or anything. So, let's go to these two, and this is what we do when that fails. Okay, so I come over here. Fluorine neutral. Antonio, how many protons do I have? How many protons, Antonio?
3.
Wait, what's the atomic number? 9. Okay, were you dozing back there? Okay, now if it's neutral, Antonio, this you can save yourself. Okay, save face. Okay, if this is neutral, you must have how many electrons?
9.
9. Good job. Good job. Okay, so 9 and 9. So now let's come down to this one. Aaron, take it. How many protons? 9. And how many electrons? 10. Okay, now there's two different ways to look at this, and either way you look at it will lead you to the same answer. Okay, let me tell you the first one. It's actually the second one is probably the more popular of the two. Okay, this, we have 9 attracting 9. So it's like 1-on-1 in basketball. Okay, you've got 9 here trying to attract 10. If it can't attract as well, think about it. You got, of course, you don't have 9 basketball players or 10 basketball players, but you got 5 guys and 5 guys. And they're playing 1-on-1 defense. Well, if one guy fouls out and there is no bench, you're playing 5 to 4. I'll put my money on the team with 5 guys is going to win. Okay, now over here. Who can do the better job of attracting? This should be able, because it's 9 to 9. Okay, so this guy can't attract as well, which means a little bigger. And so if you think of the numbers game about who can attract whom better, this tells you this is bigger. Okay, here's the opposite way to look at it. You got the same nucleus. So the tiebreaker obviously is number of electrons. The more electrons you have, the more they're going to repel and spread out. Okay? So if you got 10 electrons in this volume, they repel each other, they're going to spread out a little bit to get away from each other if they can. So if you think only in terms of repulsion among the electrons, they want to get away from each other. You go to a party, and there's a real nerd, or whatever. What do you want to do? Get away. All right? Or, got two tomcats in one room. My two tomcats used to hate each other. One is now deceased, so. But anyway, when they were both alive, they hated each other. They never came in close contact. They spread out. If they were confined to one room, they would get in the far corners away from each other. Electrons are like tomcats. They want to spread out. Okay, so I can generalize. Neutral atom is always smaller than its own anion.